Welcome to Software Development with Mikko from Literary Foundations. Today we are working on one of my projects called Optidepy, which is a deployment software that it's easier to explain when drawing. So basically, we have our computer here, let's say IDE, and we are building our development version, which changes all the time. And then we have our server and database in the cloud. This, for example, this is our test server, and sometimes we want to update the software that's on the server. So we use let's say an SSH connection and transfer the files to the server and restart the server, and then we have the new version running. So for example, if this was 1.0.3 and this was 1.0.2, so when we do this sort of connection, then we get the same 1.0.3. And the problem here, for me at least, is working from a place with not such a good internet connection, that when we have like well, let's say 10,525 small class files, whatever, Scala or Java, whatever, then the transfer takes very long. So that's a problem, especially when you're dealing with production servers. You want the process to be fast and you want to make as few mistakes as possible, because it's usually problematic when you make a mistake. At least the servers I'm working with are kind of active 24/7, so there's really no good place to make long shutdowns or anything like that. So you want the process to be as fast as possible. So that's why I created this Optidepy software. It kind of reviews the directories. Let's say there are some subdirectories here against the specific folder where it has stored the kind of release version. So it compares these two and checks kind of which files have changed. So for example, from these 10,000 files, it might find, okay, these 25 files have changed. So then it moves these files to this new location and also creates a nice little subfolder for them, so that I can take this subfolder or these 25 files and then move them to the server. So instead of moving 10,000 files, I move 25 files. That's a lot faster. The process itself takes some time because it's not so well optimized, but it's a lot better to spend that time on your local device here instead of on the server side here, because this time is valuable and mistakes cost a lot of money. This side is like, who cares if your development environment kind of you make a mistake or something. So that's the idea of Optidepy. But today we're focusing on one problem with this software. So let's take this algorithm description here and let's describe the problem. So at this time, the software looks for change files, and the first thing it does, it checks the last modified time. So that's a timestamp on each file when it was last modify, so written into. And might be accurate, might not be, but usually it is a good observation. So let's say we have 3 files in this folder, and in this folder we have 2 files, and these have changed recently, and let's say this one as well. So it collects, well, actually it doesn't collect those, it compares those in the kind of destination directory, like so, and checks like, okay, this file, does it match? Is the content any different? Is the file size any different? If so, then it moves it. If not, then it just ignores it. So it kind of adds double filtering. But the thing that activates this process is this last modified time. So now, oh yeah, and one more thing. After the deployment, the algorithm checks back these files and checks like, okay, this file here, is there a matching file over here? And if there isn't a file over there, then it moves it to the trash, destroys that file, so that we can remove files as well as add them. So let's say we didn't have this file over here, that was removed between the deployments. So now it checks, okay, there's no file there, let's remove this. Now we get to the actual bug or problem. This is a logic error in my design, and the goal today is to fix that logic error. So the logic error comes in situations where we rename files, rename directories. So let's say we have this situation, 2 files here, and this is a directory called A. And then during development, we rename that directory as directory B. We keep the files the same, but we don't modify them. So the files still have their old, this old last modified time. Let's call this A, little a. And these also have this last modified time, little a. And then we have the destination. We need some space, so let's just remove what we have here. Okay. And in the destination place, we have a directory called A, and then we have this same file here and the other file. So these are the previous version. Then this is the new version. Okay, so now we do a deployment, and it checks, okay, is there, let's call this file X and this Y. So it checks for B/X. Does that appear in the destination folder? No, there's not even a directory called B. So that, yeah, I'm messing it up again, sorry. That's not what happens actually. It checks the file last modified time first. So it checks this modified time. And as we discussed earlier, the file is not modified. It keeps the same modified time as here, which is before the previous deployment. So it checks this, and it doesn't activate the deployment process. So it doesn't even check whether the file exists in the destination folder. So the destination file would have been B/X, but because the file was not modified, it doesn't bother to check whether it exists. So no deployment is happening here. But after the deployment, it goes and checks this previously stored file A/X. Let's give this names. It checks, okay, A, well, we only have directory called B, we don't have directory called A, much less A/X, so A/X goes to trash, and A/Y goes to trash as well. So what we end up with is not creating the B/X folder and destroying the A/X files. So changing directory names currently causes a lot of trouble. Unfortunately, I haven't run into this problem in production environment yet, but it's a problem. So now we have to discuss like how to fix this problem. So sorry about the blinking. So one thing we could do is skip this thing here, and instead do the check for every single file. Ignore the last modified time. But that's kind of part of the optimization process. This last modified time, it speeds up the process a lot. So we kind of don't want to sacrifice that. Well, the second thing is to check for new directories. So the software kind of iterates, like directories can be represented as like trees. Tree is a data structure where, you know, things go kind of down always. Let's draw a tree. Okay, so this is the, let's say, root directory. Well, let's call it R. Then we have the A and B and C directories. Then we have individual files here. These don't contain any subnodes. And nodes are like these three things. Sorry for my lack of accuracy with the terms. But this is now a file tree, or, you know, some kind of representation of a file tree. So the algorithm goes kind of down the tree and looks at every single file at a time. So it first looks here, then here, then here, and then and there. And it checks the directories as well, kind of goes down the tree to each branch. Now, when the algorithm goes to the directory, let's say directory A here, what we can add is to check on a directory level whether that directory exists in the server side, you know, or the deployed version. So let's say, let's copy this, and this is our kind of deployment version. And let's remove directory A. Let's say we added the A directory. Okay, so it should check now whether this A directory exists here, and it doesn't in this case. So instead of checking the files, there's no point in checking the files if not even the directory exists. So it can just choose to deploy every file in that directory and whatever it's under that branch. So not only do we resolve this problem with directory renaming, we also fasten up the process for new directories. So we don't have to do file, you know, a singular file checks anymore. It's not like that took so long anyway, but you know, potentially faster. So that's the idea of the fix. Kind of simple. The problem is not too bad either. So let's try solving that in the development environment. Okay, so now we're in kind of development mode. And let's see where we want to go. We want to go to the deployment algorithm here. And have to say, this is not the cleanest code I've ever written. this sort of algorithm type of code tends to be, for me, very long. As you can see, this huge method here, like lots of lines of code. And unfortunately, in this case, not too much commenting either. Sorry about that, but at least we have the Scala doc. So this is a Scala software. That's my main language. So let's review the code first, so we can understand what's going on. So first it goes, we have certain data models I've added. Then there's a project which has certain bindings. It describes like what file is going where in the final product. Then we have the last deployment time. This is used in the, in checking whether files have changed or not. And then we have some settings for whether how the deployment should be made. We're not that interested in those right now. So it goes for each binding first, and a single project may have multiple source directories ending up in the deployment place. Let's say the code and then the documentation separately, whatnot. But the process is the same for each binding. So one binding binds one source to one destination. Okay, so in this section here, this pretty long section, we identify the files that have changed, stored in the value altered files, which is like an attempt of file paths. And here, as I've so nicely written, we check the file change times. So first we have the iterator. This is like the this is my custom iterator that takes all the nodes in the tree and iterates through them, like we discussed earlier in the visualization. And this is anyway, it doesn't matter. So we filter the iterated files based on if they have changed or not. So here we have the case that the file is a directory, in which case it hasn't changed. And then we check the last modified time of regular files to see if they have changed. And now we should somehow add files that appear under directories that are not present in the destination. So that's the challenge, and it should go somewhere around here. It's not in the filter function. It's kind of adding things, so we kind of have to modify this a lot. So let's add a to-do there. That's the place we want to kind of work on. And let's see. Oh yeah, this one filters further based on like whether the files have actually changed. So that's the process we described earlier in the visualization. And if time threshold wasn't specified, then we target all files. That's okay. That this case we can just keep, because that's basically the first deployment that moves every file. So that doesn't change. That's not affected by this bug, I don't think. Then we kind of transform the files into relative files or something. Yeah, bindings. Anyway, that's a different story here. Here we kind of move the files to the deployment directory. So right now we need to add files based on whether the directory has changed, and while keeping this logic. So I think we should kind of make the code a bit cleaner as well, and create a new method. So this is the structure right now. We have the check for remote files, handle file deletion, and a check function that checks whether the file has updated or not. You know, if the contents have changed. So let's add one function here, which is private def. What shall we name it? Find altered files. And then we have, let's see what kind of stuff we need. We need at least the binding, which is of type, well, binding. So, but actually we need I think we need the absolute binding so that the destination directory is correctly bound. So it moves to the actual full destination. That may be unclear to you, but basically where the files actually will exist, so that you can check whether they exist or not. And file-specific binding was a special use case, which I guess we have to cover here. No. Yeah, we need to cover that. Okay, but that doesn't matter. So you can actually accept this iterator here, as well as the, no, we need to know the paths. So let's start with this. Let's assume we have absolute binding and do this sort of stuff. Okay. So let's first copy the code over here. I don't know if this worked or not, but let's see. So now we have this absolute binding. Okay. So we can use this absolute binding in place of the binding because it just altered the destination folder. It doesn't affect the source property, so we can just use this. And also we need last deployment option deployment, I think. Yeah. And then source is the same, source is the same, source is the same. Okay, let's see if we can get the errors. Okay, we're missing the logging function. Let's add it. Exit logger. Okay. So this is just a logging interface I've created that's passed implicitly here. I'm not going to explain right now what implicitly does. That's not important for this operation here. We'll look at that another time. Then we have the source again and source again. Okay, so now we are basically move this piece of code to a separate method. So this alone helps to make the software a bit more readable, because this method here describes what's happening in this block. So we accept binding and the deployment, basically to get the deployment time, and we get an output of the files that have changed, the files that should be relocated to the destination directory. So we keep this one, but we cannot use this part here because we kind of need to iterate the tree in a bit of a different way. We might stop the iteration, so we might have to do a manual tree iteration instead of just iterating tree. So we might end up using recursion. So now we need to kind of figure out how to actually create the iteration process that goes through the tree. So we add some directories and some files. You know, the tree might be, let's add another directory here, another here. Might be deeper, but you know, for the purposes of this algorithm, it really doesn't matter what shape the tree is. Okay, so here's the tree. Now let's imagine going through that tree, and let's say that this folder here didn't exist previously, and let's say this file didn't exist or was modified, and these were not. So basically we start always at the root here. Let's root. This is the root of the tree. Trees are, at least I draw them like upside down because you start over here. So it's usually the normal reading order from up to down. Although the opposite direction would look more like a tree. That was not useful information, sorry. Anyway, first we go to this file and check, did it change? No, it didn't change. So we need to continue and check here. And that's kind of the last of the files, nothing changed. So we go back up and go to the next file instead. Nothing changed here, neither, so we move to this file. So here, go down, and this time we notice, okay, here's something changed. So we take this, and we kind of, because we're not using the iterator approach probably right now, we need to create some sort of buffer where we can move these files. So we move these two files into the buffer over here. Okay, now we have dealt with this directory, so we move to the next directory and check whether something has changed. And there we go over here, and we notice, okay, this one changed. So we move this one as well. So in the end, we have a buffer of 3 items. We of course don't know how many of those are there usually with the buffers, but then we can just create the vector containing the 3 items, and that we can pass as the return value. So return the value of the buffer after iterating through the tree. So that's the plan. Let's focus on a bit more on what happens at each step. So obviously at every directory we have to check whether this directory exists in the final destination or not. So we compare with the target directory. So we have to resolve the target and then check exists, whether the target exists, and do stuff based on that. For normal files, we follow the same process as we used to. So we check the last modified time first, and if that has changed, then we compare the files with the destination file or target file, and then we decide either to keep the file or move the file. So we have different process for directories and different process for files. Also, we kind of have to iterate through the whole tree, but here we don't go to the files, or we don't do the normal process for the files, we just move them. So this is yet a separate process. So we have process A, process B, process C. I think that will do. Let's return to this design if something comes up, but let's start with this one. So first we need to find a way to iterate the directories, and that's better to be done in a separate method because we're going to be using recursion. Recursion is when you call the same function within that same function. So the function may call itself again, Again, let's draw a recursion before we continue. So here we have a function, and within that function code, it calls the function itself. So it goes back to the code. Recursion is a nice way to get into trouble, because you can do infinite loops with it. But usually you want to kind of find a stop condition that this is like if condition A, but if not, then finish the function. So eventually it will get here and stop. That's the basic idea of function, and at least in my experience, whenever working with trees, recursion is the go-to option. So we do I think this is directory specific process. Find over files from directory, and input is tree. Let's use the Flow version. Flow is the library that I've developed. I like to use my own classes. Node tree. This is tree that contains paths, and then so first we need to check the directory exists in the target destination. So how do we do this? So we need the relative path to the source directory, and then we need to form the target directory based on that. So obviously we need the source and the target directory, so we need the binding. Let's do binding. Okay. So let's first check whether the directory exists in the target. So first we need the target. We cannot get the target before we have the relative directory. So relative path is directory node now, which returns the wrapped path relative to binding.source. That returns the relative path, and we use either here. These either and relative to functions are custom-made functions. This one's found in the, well, both are found in the Flow project. This one's from the collection extensions, and this one is in the file extensions file. I will not go there right now, but it just returns the part of the file path that's relative to the source directory. So easier to show than to explain. So we have, let's say, A, B, C. This is one path, and the C is like the directory we're working on right now. And let's say we wanted the C relative to, I don't know, let's say A. That would yield B/C. So it would remove anything before this A part. So we could even have like root/A/B/C and use C relative to A. That would still return B/C. So it's just transforming the paths. So let's say we use C relative to root. We would get A/B/C, and then we could use that to determine the target directory. So we took the ABC and then just add target/ a/b/c. So this is the directory in the target that matches the directory C in the source. That's the idea. So that's the relative path, the B, A, B, C. And now the target is just binding target / relative path. Kind of easy. This one's also enabled by the file extensions functions. And now we have the target directory, so now we check whether the target directory exists or not. So if target directory exists, then we do the normal thing, and if not, then we do something else. So let's write it first. Case if the target directory exists, we compare the files one by one or move down in the tree. And then the target directory doesn't exist. We just add every regular file under this directory to the deployment. So like so. I like to kind of add comments here to describe what I'm doing. So the next time I'm coming to this code, I can review the comments and remember what I was thinking. That's why there's kind of lots of comments here, which for me at least is important, especially in these more complex algorithms. Of course, you know, you get to decide whether this is complex or not, but for me it is somewhat complex. So it's better to read text than code. Of course, you should make your code readable as well. And right now I remember that we also need the buffer here. So deployment files builder, this is vector builder that contains paths. Okay. So in case the target directory exists, we go to the previous thing and kind of, we don't have file specific binding here. I think we can keep the file specific binding use case separate because that doesn't involve any directories, just it just targets one regular file. So we can handle that here in this function. But let's assume here that this is actually a directory. So so we move down. Let's see. That means that we separate the directory files into normal files and directories. For directories, we have to use recursion. For normal files, we can just use the manual stuff. So let's do that. So we have, let's say, make this more readable. Directory is directory node /now. Replace it here. Then we have directory children. Actually, no, we use directory node dot children and divide by dot now is regular file. Okay, and then we move it to tuple, whatever, how do you pronounce it? Sorry for my English. So we have the non-regular files. These are subdirectories, and then we have the regular files, subdirection, directories, and yeah, let's use camel case. Kind of hard to speak and write at the same time. Subdirectories, and then we have the files directly placed under this directory. So both are kind of in tree format still. So this one again is from collection extensions, just divides the collection into sub-collections. Here, subdirectories and normal files. And for files, we do the normal checking, which we kind of can copy here. So we use this last modified thing. I think, yeah. So files, filter, let's just use iterator, map them into normal files. So use the nub function. This is a file, okay. Then we compare the last modified time. Again, we're missing the log. Missing logger. Okay. We need the log. And then, oh yeah, we need the deployment time as well. Binding. Deployment option deployment. Okay. So we just pass the same parameters to this function so that we can make the comparison. So instead of D like deployment, we have last deployment. Oh yeah. And we assume we have deployed this project previously, as we mentioned last time. So we have the timestamp of the deployment. Here we check that, okay, this file was modified, so we include it. And here we have a problem, or actually we check whether we include it or not. And here we have problem reading the timestamp, so we log the error, and then we assume it has been modified. This shouldn't happen too often, but there might be some file read problems always. Okay, so that's the first filtering process. Let's make this a bit nicer looking. Okay. And then we add another filter function from the previous code. Which, like here, checks. You can actually just copy this. Copy this here. Oh, we have successes and failures. Well, let's just say we have. Let's use the word file instead of path for now, because there's regular files. Oops. And just replace the path with file. Okay, and this was the binding, and this is the binding. Okay, so we just copy the code over here. We have used this before, so we kind of know this works. Let's comment this one as well. Checks which files have been modified since the last deployment, and only includes those. Then we filter further. Okay, this is now the normal files process. We also need to add them to the buffer, so we can use, let's just use for each for now. I don't know if this is the most optimal, but it shouldn't matter too much. So deploy whatever, and finds builder. Let's add it to the builder. So here we actually add the file, every modified file, to the deployment. So let's actually comment this. Add, change, modify files from this directory to the deployment. Okay. Now we have handled the files. Then we need to also handle the subdirectories. So handles the subdirectories using recursion. So for the subdirectories, we just follow the same procedure further. So need to call the same function, find altered files from directory. We use binding as deployment. Then we use the, well, not quite, subdirectories for each. So we handle each subdirectory separately. Subdirectory. And for each subdirectory we add this process. So subdirectory, and what else? Deployment files builder. Okay. And as you can see, we have the log parameter here. It automatically gets assigned to this function, so we don't have to write it again. That's the good part of the word implicit. So now we have handled the subdirectories as well. Kind of neat from the IDE to tell us that this uses recursion here. And that's it. That's the directory case handled. So, oh yeah, we need a return type here. This function doesn't return anything. It just puts the files into the deployment files builder. So you don't need to return type except unit. Now the case where the target directory doesn't exist. So here, move all regular files to the deployment. That should be very easy. So we take the just replace this because we didn't use this directory anywhere else. We can just like this. So directory node, iterator. You know, it's below iterator, sounds good. Map filter is regular file, and let's add all of these to the buffer. So deploy files builder. Okay, so we add just a nice one-liner. Not implement, because my IDE is starting to kind of get stuck here. Anyway, I'll just explain what happens here. So we iterate all the nodes. That means all the 3 items under this directory. So any subdirectory, any file, those will get iterated. And we're interested in the paths themselves, so we call nav. Mapping just transforms the type of the iterator in question. And then we only take the files that are kind of regular files. We ignore directories because directories get auto-created in the process anyway, so we didn't have to move them. Moving them would actually be kind of challenging. So, and then here we just add all of them to the builder. That's what this line does. Kind of what it says. Okay, so now we have this nice function that handles all directories. So now we just need to call it. And I'll just copy it because it has so many parameters here. And paste it here so I can remember what's going on. And again, sorry if the screen's hard to see. Hopefully you can at least enjoy the presentation. So let's handle this file-specific mode separately. So if is file-specific binding, do something, and if not, let's do the normal thing. So file-specific binding means that the source is not a directory, it's a regular file. Here we can assume that it's a directory, so let's write that case source is a directory. Processes it and collects files to deploy. So at least I know we need this builder. So deployment files builder, new vector builder path. Okay, now we have the builder. Do we have the binding? Yes, we do. As deployment, we have that. It's called here D. I'll just rename this deployment. Better, more readable. Okay, so now we just call find altered files from directory, absolute binding, and we have the as deployment, just deployment, and then we have the directory, which is the source. So absolute binding source, which we need to convert into a tree. So let's do that first. And then we have the deploy files builder. So we need to form the tree first. Let's do that. Source, and I have a nice method for this. This is to tree, and that creates a lazy tree. So we have the, actually we could just use this. We don't need the tree elsewhere. It's a lazy tree. Isn't that whatever? It's kind of annoying that they don't implement the same interface. They're basically the same thing. I should refactor that at some point, but it's like tree like, oh, horrible. Just lazy tree. Oh, sorry about this. Is a problem in my library. There should be a one interface called tree that would, you know, that both the tree, normal tree, and the lazy tree would return. Kind of not nice that they're separate. Actually, let's just add a task for that. So add a common interface for tree and lazy tree. Okay, just so that I can remember it later. We actually have here the trees, and then we just return deployment files builder result. Okay, that's the case. Then case source is a regular file, checks whether it has been modified. Okay, so here we need the last modified time as well as the file checking. So basically we have this same filter process. So now we could write this all over again, kind of copy paste. That would not be nice. That would not be readable. I mean, this is not very readable as it is. So it's better to separate this into separate methods and to call those methods so that we can just check them, and we can actually kind of combine these two filter functions while we're at it. So let's take these filter stuff and add yet another method. So has updated. Let's make this f has changed something. I don't know even what has changed yet. Just file. Just file path. Okay. We can remove this, and then we'll do the filtering later. Secondary filtering. So we are missing the last deployment. This is deployment again. And then we're missing the log. So implicit log again. Just moving stuff around. Okay. So here, if the last deployment time has changed, then we add some additional checks. Otherwise, the file certainly hasn't changed. So, okay. And here we actually, okay, so we cannot do this. Just modify change. Let's store the result into a variable, or this case constant, and then check do the additional kind of check if that condition is found. So if last modified was changed, then we also do this. Then we also do this secondary check. Sorry, I have a hard time writing and speaking at the same time. So we do this, and then else false. If the last modified time hasn't changed, the file hasn't changed under this assumption. Of course, in the beginning we found out why this assumption might not always be true, but it kind of makes things faster so we can make it. So now we have the binding. Binding is required, so let's apply binding. Okay. And now we have just separated this method, and this has changed because this has updated, which is this is a bit confusing because they're basically the same name. So we kind of have to do something about that as well. So what this does, it tests, maybe we can rename this into file content has updated. Okay. So that's more specific. This just checks whether the file has changed, and it might not check whether the file content has updated or not. Might. Okay, we have the has changed method. So let's go to where we copied it from. That was find other files from directory. So we just use filter has changed, and we have binding file as deployment. Okay, so we can just remove this piece of code, and look how much nicer this looks. So much smaller method here. So, and let's just do this one as well. Let's add them all to deployment buffer. So what we did was that we delegated this, instead of writing the filter here, we just call this hasChanged method. This underscore here just refers to the input parameter, which is the file. It's part of Scala syntax, which you probably know if you're watching this. Do we need a comment here? Not really. This is relatively readable, so that's good. Then we go back, file specific binding. So we check if so has changed, absolute binding, then the file, which is absolute binding dot source, then last deployment, which was named deployment. Okay, so if the file has changed, we return a vector that contains that file. And if not, we just return an empty vector instead. Okay. So this now returns the vector that contains the modified files. So we can remove all of this stuff. And let's see, what does it return? Equals serializable. That's not good. Oh, you're not seeing it. Well, here there is equals with serializable. That's not what we wanted. So the return type has changed, probably because we're not returning a try here. And this one's returning a try. So this one might fail. So we can either choose to not return a try here, just log the errors, or we can return a try here, which always succeeds. But let's first see where this one should be used, kind of to see which approach is better. So we use try flat map here. Try flat map that terminates when something fails, which I guess might be appropriate when we're talking about deployment. So let's return a try. So here, let's just store the return value into modified files equals this all stuff. Some line breaks here. Okay, so now we have the modified files vector, and we just return modified files success. And here, where is it? The tree, this function. This can kind of mess us up because this one uses the logging system. So it just logs read errors. So that can cause that some read errors go unnoticed. So what we could do here is to kind of use a specialized logger that will kind of catch the error and cause the process to fail. But we won't do it for now because that's a separate kind of project. Right now we just take the risk. So use a separate logger that fails the process if an error is encountered into tree. So this way we can actually fail the process instead of always succeeding. Okay, so now it returns, as you can see, returns a try vector path as we expect. So let's just add some comments here to tell what this method does. So what this does is it finds all modified files from the specified binding. Finds all files that were modified since the hash deployment from the specified binding. Okay. That kind of reminds me later what's going on here. So now, and this by the way, this process is a lot of refactoring as well. So refactoring is something where you kind of rewrite code like we did with filter function stuff, making things more beautiful, making things work better without kind of altering the function. Here we are combining this with altering the function by adding this kind of bug fix or workaround. So so instead of now altered files, we can just remove all of this stuff and assign find altered files, which accepts binding last deployment. So absolute binding and last deployment. Okay. So instead of all that code, like all this stuff, we now have this one-liner here. Makes things much more readable. So what happened with the is file specific binding? We already have that in that. And actually this one's not so useful as well. You can just replace this like this, because we don't use it elsewhere. Okay, so we don't need this constant here, and even the absolute binding, we use it only in one space, so we can just pass it here. Okay. Everything the right output correct. Okay. Let's just add a comment on what happens here. Actually, this might be more readable if we assign a new variable for it anyway. So absolute binding. Just use it here. This is easier to make sense of later when we come back. This one's easy. We don't really need this special assignment here. We can just process the stuff later. Let's remove this thing. And so what happens here? This is one of those lines where you go like, what's going on here? So we transform the success or the failure by transforming each path to something. What's going on here? We transform into the bindings. So like file specific bindings. Okay. Interesting. Yeah. Let's add a comment that says that so that we can remember that later and not have to do that work again. So forms the modified files into file specific binding instances. Okay. And then just processes the other files. Okay, so this part can remain as it is. So what do we have here? We have added one to do for later. Let's just optimize the imports. Okay, so that's the that's the change. Let's see if it builds. Need to build the Utopia library as well, because it probably has changed in between or since I last modified this project. Okay, everything builds, looks good. Let's go ahead and document this change. Bug fix. Deployment algorithm now takes into account renamed directories. Okay, so that's the programming part done. Next, we need to test it. So let's build the artifact, and then I need to test whether this works in actuality or not. Right now I don't have enough test data for this, so let's do that later. You found out how this process went. So let's just recap. We explain what this Optidepy algorithm does, and we identified this process of using the last modified time, which caused this bug of things going into trash. So we designed this new algorithm that checks for changed directories. And we added all the changed files to the buffer, and then returned that, and then continued with those files. And we used recursion in this this and in the code we modified the deployment algorithm here. We added this find altered files method, and for that we created this recursive find altered files from directory method, which handled the case where the file is a directory. So that's this use case here versus it covered the case where the directory exists, which is this use case, versus where the directory doesn't exist, which is this use case. So we separated the program logic there, and for directories we used recursion, and we also checked for modified files, and for changed directories, basically, renamed directories, we added all files without checking whether they were modified or not, because they couldn't exist in the target directory, because that directory doesn't exist. And for that, we separated this has changed logic here into a separate function, made it a clean, nice method or function, renamed this conflicting function name, and used this has changed in the special use case where the binding targets a single file. So, a single jar file, for example, or something, instead of like moving all files from a directory. Kind of a simpler use case, as you can see, it's very simple. So we use the same has changed here. So basically, if we review, instead of having this huge function which covered like this much space, now we have just a very simple piece of code here, and that calls a somewhat simple method. So things became more readable, and I think that's it. I hope you enjoyed watching me do some software development. I hope to see you again. Please send me feedback and stuff. Share your thoughts in the comments, and see you next time.